section of a discussion of polynomial functions. We're going to start talking about the concept of graphing polynomial functions. And so in this video specifically, we're just going to go ahead and talk about the concepts here. Nothing involving mathematics or anything like that. We're just going to really just talk about the ideas behind how we would normally approach graphing polynomial functions. And as I just mentioned, here's a preview of what's going on. We're just going to have a discussion on how we can graph general polynomial functions. And finally, some prerequisites for this section of lecture here. You have to kind of know what a function is. You have to know all about functions, in fact. Domain, range, all that fun stuff. You should be very familiar with polynomials. And you should also be very familiar with graphing. The things about polynomials you don't need to know right now, because we're going to be discussing them, is how to graph general polynomials. But other than that, we're going to spend quite some time over the next couple lectures actually graphing them. So let's go ahead and focus in on just a general polynomial function. And when I say general, this is technically not general. This is a specific polynomial here that I'm giving you. P of x is equal to 0.12 x to the 17th plus pi times x to the 14th minus 1/2 x to the 5th plus x squared minus 3x plus 1. Okay, that's some polynomial that somebody's come up and handed you. So it's very specific. But you can imagine that I just randomly chose these numbers. Remember, what makes a polynomial is the fact that all the powers on our variables are natural numbers. So if you look at all our exponents on our variables here, they're all natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. There are no fractional exponents, and there are no negative exponents on our variables. So that's very important. That's what defines a polynomial function. So now that we see we have a polynomial function, I want you to also note something that we've already said about polynomial functions in the past. What can we plug in for x? That is, what is the domain of this polynomial function, or any polynomial function in general? Well, you can see that it doesn't matter what I plug in. I can plug in x equals 0. That's fair game. X equals 1/2. X equals 0.82572. Any number I want, for x, I can plug in, even negative numbers. So it turns out that, and as we've mentioned in the past, it turns out that the domain for a polynomial function is a set of all real numbers. And we denote that with a capital R with another vertical bar there. So two vertical bars on the capital R. That means a set of all real numbers. So this gives me an idea, since we're going to be talking about graphs of polynomial functions. This helps me identify values I can plug in for x. So a polynomial function is a very special kind of function where if we were to try to graph it out, and I'm not telling you that this is what the graph looks like, but at least I know that I can plug in, let's say, x equals a -7, and I'll get some output. And I can plug in x equals 0, and I get some output. And I can plug in x equals 5, and I get some other output, or something like that. But I can keep going all day long. So I could plug in any x value I want. What I expect to find is some type of smooth curve. By the way, this is, oops, I missed my value there. This is not the graph of p of x. So this is just a little note here. This is not p of x. It's not the graph of that function. However, I just want to illustrate that it does have this nice behavior that we can plug in anything we want. In other words, there's no missing or no gaps in the graph. That's the first thing to note. Second thing to note is there are these special features at the end here, this side and this side. It might just be that we can find out what the graph looks like in the long run. In fact, let me go ahead and give you an idea. There's actually three very important parts to a polynomial graph. So these are the three key regions to the graph of a polynomial function. The first key region is basically the behavior of the polynomial function as x approaches negative infinity. In other words, as x gets very, very negative, what does the graph look like? By the way, this notation, the behavior as x approaches negative infinity, will look like this in most textbooks. as x approaches negative infinity. That's x, a right arrow pointing towards negative infinity. So as x approaches negative infinity, there's some behavior that happens. So we'll say y behaves a certain way. Then we have the behavior as x approaches positive infinity. And notice I have this gap here. I have the three key regions. We have region 1 and region 3. The reason why I skipped region 2 is because that's kind of in between region 1 and region 3. It's a little easier to talk about regions 1 and 3 first. So the first region is all the stuff where x gets really negative, and the third region is all the stuff where x gets really positive, and then we have all the stuff in between. So that's the second, or the middle region, is the stuff in between, or the stuff between, I suppose you should say, actually. So these are the three key regions. The first and the last one here are what we're going to focus in on for one lecture video. And in that middle section, the stuff between, will be another lecture video. But that's really how you zoom in to graphing a polynomial function. You concern yourself with what we call the end behavior, and then you focus in on what I call the middle behavior. So you have the end behavior and the middle behavior. Now, as a simple example, and because we're doing the conceptual lecture here, I'm not really going to do very much with this example, but as a simple example, suppose that this graph represents some polynomial function. Now, you have to trust me for the moment that this can represent a polynomial function. In fact, polynomial functions tend to have this look to them, that they're kind of nice smooth curves, and they either rise continuously as x goes to negative infinity, or they fall continuously as x goes towards negative infinity. And the same thing as x goes towards positive infinity. Either they continually climb or they continually fall. So this could be some polynomial function here. And like I said, I'll call this p of x. So let me go ahead and write that down, p of x. And we see that as x goes to negative infinity here, in other words, as x gets really negative, this might be x equals negative 20, this might be x equals negative 50, and so on and so forth. We might see that as x goes to negative 1,000, it's super tall. The y values are super huge. So as x gets to negative infinity, we find that the y values are also approaching positive infinity. So looking at this right now, and notice my notation here. As x approaches negative infinity, the y values climb. There's a couple ways this could be written. Y approaches positive infinity, or some instructors really like p of x approaches positive infinity. It really doesn't matter. They mean the same thing. Y is the outputs p of x. And then the other thing to note is that as x goes in the positive direction, so to positive infinity, that's this region over here as x gets bigger and bigger, the y values, well, as I look at this graph, they're falling. They're getting much, much lower. In fact, they're going down to negative, this height right here might be at a negative 50. The height as x gets even bigger might be a negative, let's say, 80, and a negative 300, and a negative billion, whatever it may be. So you see we have that the y values are approaching negative infinity. And like I said, some instructors might want you to use the function notation that p of x is approaching negative infinity. That means the same thing. So this is how we determine the end behavior, or in other words, this is kind of our description of the end behavior of this polynomial. Now, the only thing else that we really need is to determine the middle ground behavior. And that's a little more difficult, and that's why I said that it's going to be broken up into two lectures. But essentially what we're going to find is what is that x-intercept, what is that x-intercept, what's this x-intercept, what's this x-intercept, and what's that x-intercept. That's the stuff that happens in between x being really negative and x being really positive. It's all the middle ground stuff. If you can find out what the x-intercepts are, it really does help to graph a polynomial function. And when I say graph, we're really just sketching really quickly by hand a polynomial function. Now, as a simple example, again, and I said that our last one is our last example, but actually, I'm going to make this one our last example. Let's suppose you want to graph a polynomial function that has the following end behavior. So let's make the end behavior, I don't know. Let's say that as x approaches negative infinity, that the y values will approach positive infinity. And as x approaches positive infinity, the y values also approach positive infinity. And let's just pretend that the middle behavior, and there's going to be more to this middle behavior later on, but for right now, let's just take the basic middle behavior, which is that we have some x, we're going to go through our x-intercepts. Let's just pretend the middle behavior, we have x-intercepts at, let's just say x equals 3, 0, negative 5, 0, and we'll do one more. I don't know. Actually, let's do two more. Let's do 4, 0, and 8, 0. Now, the first thing you should do is plot those x-intercepts. And the second thing you should do is go ahead and write the end behavior. What do I mean about write the end behavior? Well, let me do this in blue. The end behavior, let's see, as x gets really negative, so it's in this negative direction, all these x values over here, okay? The y values are super positive, so they're climbing out here, let's just say. They get very positive. And then as x goes in the positive direction, y also again goes very positive. So it's something over like this. So notice that these arrows just indicate that the graph is climbing as x goes negative, and the graph is climbing as x goes positive. And the behavior in between can be determined from these x-intercepts. So what I'm going to do is I have to kind of climb, or fall in this case, down to this x-intercept. And now I'm just going to pretend for the moment that I know it's going to cross through it. Climbs back up, crosses through this one, climbs back down, crosses through that one. Let's just make sure it looks like we crossed through. It doesn't really, but I'll adjust that. And then it climbs back up and crosses through this. And then climb up forever. That's the basic sketch of a graph, a polynomial graph, or the graph of a polynomial function with this behavior. Couple things I want you to note. This is a smooth curve, or supposed to be. Because it's a function, it does not do this business. Right? It can't double back on itself because then it's not a function. It doesn't pass the vertical line test. So please note that. Also, if it crosses through the x-axis and there's another x-intercept, it'll eventually bend to go back up to that next intercept. So like in this case, it went through a negative 5, and now I know that ahead of me, I'm going to have to get back to the x-axis at x equals 3. So I'm going to start bending and coming back to the x-axis, which occurs at x equals 3. And now that I've gone through that, I know that I'm going to have to bend back down very quickly to get down to the x-axis at x equals 4, and so on and so forth. Now, I do not want you to think that it's always the case that it goes through the x-axis. Sometimes they bounce off the x-axis, but that is a discussion for the actual mathematical lectures, not the conceptual lectures. So we'll worry about that at that point. But what's important here is that you recognize there are really 3 regions that we worry about. Again, the end behavior as x gets very negative. So in this case, we found out that forced the y values to go positive. The end behavior as x goes positive, we were told that the y values are positive there. And then the middle ground. And the middle ground, again, is the more challenging information to get. It's not super difficult, depending on the function. Most functions are pretty impossible, but the functions that you'll find in a textbook usually are pretty okay to figure out. But that should do it for the conceptual lecture.